Welcome back to the next video, everybody. Today, we're going to look at flatness as a deformation condition. More specifically, we'll introduce the idea of flatness as a deformation condition, and we'll look at it again more specifically later in the chapter. So the setup is this. We'll refer the reader to Ramakrishna's thesis on a variation of Mazur's deformation functor, RVM, throughout the rest of this video. We'll fix a coefficient ring lambda and a profinite group pi. We'll let rep lambda of pi denote the category of lambda modules of finite length, which are endowed with a continuous lambda linear action of pi. We'll let cal p be a full subcategory of rep lambda of pi, which is closed under passage to subobjects, quotients, and direct sums. That should sound familiar to you if you've been paying attention this chapter. Proposition 21, for any natural number n, let cal p fn denote the full subcategory of the category fn. What was fn again? It was pairs v comma a, where v was a rank n a module equipped with a lambda linear continuous pi action where pi is some profinite group. So we're going to look at a full subcategory of that cal p f sub n comprising those objects a comma v, such that v, when viewed as a lambda linear representation of pi, actually lies in p. Then pfn is a deformation condition. Okay, so you can see CSS page 293 for this. So in particular, if the full deformation in problem is representable, then we have near representability here, and so on and so forth. Okay, our main case of interest is when pi is GQS. So we're looking at the full Galois group of Q, kind of unramified outside of finite set of special primes S. And the condition P on our representations will be that of being finite flat at P. So we'll give a brief discussion of this condition for pi equals GQL, where L is a prime not equal to 2, toward the end of this chapter. And then I have a whole chapter, chapter 13, with more on this condition. Explicitly, we'll let cal p equals cal p sub m be the full category of rep GQL, whose objects are those GQL representations, whose representation spaces are isomorphic to those GQL Galois modules, which are generic fibers of finite flat spec ZL schemes. In other words, the representations are finite flat at L. Then P sub m is closed under passage to subobjects, quotients, and direct sums, and so it's a deformation condition. So this is what Ramakrishna proves in his thesis. Okay, what's the tangent space under the more generic setup, not necessarily specifying? Fixing a full subcategory cal p closed under subobjects, quotients, and direct sums of rep lambda of pi. By the above proposition, cal p determines deformation conditions for each n and n, right? Therefore, whenever we have a coefficient lambda algebra A and a continuous homomorphism rho from pi to gln of A, such that v equals v of rho is in rep lambda of pi, the deformation problem cal d sub rho obtained by restricting to deformations whose finite length quotients actually lie in cal p, the thing we care about. This is nearly representable by proposition 19, like I was just saying a second ago. And hence, as it has a tangent A module, T cal d of rho, which remember has a cohomological interpretation. It's isomorphic to what we called H1 of cal d of pi endomorphisms of v. And this is some like subgroup of the cohomology group, all of H1 of pi of nb. The question is which one? Well, you can also think of things in terms of extensions, right? So we talked about this already. In terms of the description of H1 pi nb as an X group recently given in previous videos, there is a direct categorical description of H1 sub d of pi nb as follows. If you take v and v prime to be continuous A bracket pi modules of finite length is A modules, by the way, which as A bracket pi modules are actually elements of P, the deformation problem. The subset extensions with respect to A bracket pi and P of like V by V prime inside the full X group A bracket pi of V by V prime of extensions, what, epsilon. So what's an extension? It's an exact sequence, 0 to V prime to epsilon to V to 0. So the way I think about this is like you get V by taking some bigger thing and quotienting out by the other thing, V prime. It's an extension, okay? So when we're looking at this subgroup of cohomology, which epsilons do we take here? We take A bracket pi modules that are members of P. I mean, it's kind of the exact answer that you think it's going to be. And this is, I mean, you have to check this is actually a sub A module of X A bracket pi of V prime, but you can check that by just adding two such extensions by restriction of epsilon 1 plus epsilon 2 to the diagonal and V plus V, and then just passing to the quotient by the diagonal and V prime plus V prime. Now, why does this actually work? Why can you actually do this? Remember, the key thing about P is that it's closed under, what do you know? Direct sums, subobjects, and quotients, which are the three things it needs to be closed under for this to actually work. Okay, so does this play nice? Do we have a little functorial commuting diagram of inclusions here like we do for H1? Yes, so proposition 12, let's let V and V prime be continuous A bracket pi modules of finite length as A modules. Then there is a commutative diagram that you expect there to be. You know TD row sits inside T row. You know each one of those things are isomorphic to some X group, the former to X A bracket pi P from V to V prime, and the latter to X A bracket pi from V to V prime. The question is, if you put the natural inclusion on the bottom here, does this diagram commute? And the answer is, of course it does. And this is really actually just the above discussion we had along with proposition 18. Okay, so what we're going to start doing now is we've finished a lot of the generic deformation theory. We're going to specify starting next video. We're going to go back and we're going to actually look at Galois representations, okay, and apply a lot of what we've learned. So I'll see you then. Thanks for watching.